Hari Om. In this video, we discuss the kinetic theory of gases. Actually, this kinetic theory is based on certain postulates called kinetic theory postulates. There are many postulates there, but I consider the main postulates. The first one is all gas consists of identical, minute, elastic particles called molecules. Second one is that all these particles are moving at random. They collide with each other and also with the walls of the containing vessel. Third one, all these collisions are instantaneous and elastic. Next one is the size of a molecule is negligible as compared to the volume of the containing vessel. And the force of attraction between the molecules are negligible, or there is no intermolecular interaction between the gas molecules. These are some of the main postulates of kinetic theory of gases. Only postulates they are. They can be proved wrong also. For example, the size of a molecule is negligible as compared to the size of the or volume of the container. There is a statement like that. This statement can be proved wrong because if the size of the container goes to very small size, then the size of the molecule becomes comparable to the volume of the container. And another wrong statement is that there is no intermolecular interaction. But we are having gases liquefied, cooking gas. We are getting it in the form of liquefied or liquid form inside the cylinder. So if gas can be liquefied, that is possible only if there must be some interaction between the molecules of the gas. Okay. And a most important statement of this kinetic theory is that the absolute temperature of the gas measures the kinetic energy of the molecule of the gas. That is, temperature increases, the kinetic energy of the molecules is increasing. So these are some of the statements or postulates of the kinetic theory, but we here concentrate on certain formulae. So we start with equation for pressure of the gas. To introduce with pressure P equal to 1 by 3 into m by v into v RMS square. There is a formula like this. The m is the mass in kilogram and v volume in meter cube and VRMS is called root mean square velocity of the molecules of the gas. Root mean square RMS. So these are the factors coming in the equation for pressure of the gas. Derivation is not required, therefore I am going straight into the equations. So, this equation can be rewritten as 1 by 3 into mass by volume. I can take it together as rho, the density, into V RMS square. Therefore, we can have the RMS velocity, V RMS is therefore is equal to square root of 3 times pressure divided by density. There is an equation for RMS velocity we have. So this is the equation in terms of pressure and density of the gas. And let us see what actually this RMS velocity is. RMS velocity, as it is stated, root means square velocity. It is defined as the square root of the mean of the squares of the individual velocities of the gas molecules. Square root of the mean of the squares of the individual velocities of the gas molecules. So as we have stated that the molecules are moving at random, so it must be having infinite number of different velocities. So let us assume the mathematical form of VRMS as, suppose I have velocities V1, V2 and V3, three velocities for the molecules. Then what is the RMS value of these three velocities? So VRMS can be stated as square root of the mean of the squares, that is V1 square plus V2 square plus V3 square divided by 3. So this is what the mathematical meaning of what you call RMS velocity. But this way, to find the RMS velocity becomes difficult because if you take one mole of the gas itself, it is having Avogadro number of molecules here. 10 raised to 23 numbers of molecules. They are moving at random means each and every molecule will be having dozens of different velocities. Therefore, this kind of calculation of RMS velocity is not possible in practice. So, we have to depend on equations like this, that V RMS is equal to square root of 3 times P by rho. So, if you have the pressure and density of the gas molecules already known for the system, then you can straight away substitute into this and find out the RMS velocity. Okay? But there is a problem. In this equation, what will happen to the density, what will happen to the RMS velocity if the pressure is doubled? I am doubling the pressure. If I double the pressure of the gas, what happens to the RMS velocity of the molecules of the gas? It is quite simple. There is nothing that is happening to the RMS velocity, because if the pressure doubles, then density also doubles. Density also doubles. So as the pressure doubles for the given gas, then the density also doubles. That means P by rho remain constant. Therefore, you can say for a given mass of gas and a given volume, if you consider, then RMS velocity is independent of the change in pressure of the gas. Okay? So this is a very important thing we have to understand. So we started with the pressure equation and we have come up to the RMS velocity equation. So Let us continue with the RMS velocity in the next video.